Alright, this is the Tutor Wizard. Welcome back. What we're going to do today is we're going to do Calculus 2 type problem, parametric curves and polar curves, basically is what we're going to do. Polar curves are basically a special type of parametric curves. Basically what's happening is all the way through calculus thus far, and basically K to 12 also, what they've been doing with calculus has been they've been taking the rate of change and doing the calculus of variation of curves in the plane. I see a visitor. Just hang on a second. No, you're getting in there now. You're gonna try and mess with everything. We're gonna do polar curves. See, that's regular graph of a single function, and well, that's the ceiling. This is a parametric curve that loops and intersects itself. Very interesting. I know that's the audience. Okay, that's Petra. She's messing with the lighting in the background. Gummed up the works, Petra. What we've been doing in calculus so far is looking at the calculus or the derivative and rate of change and a bunch of rotating them, and all these things we've been doing with functions are we've been using curves, which we're going to call gamma. Turns out those gamma functions or the curve in the plane have all been really nice, well-behaved ones where for every point x it passes the vertical line test, so that the curve gamma, we're going to call it, is the graph of a single function y equals f of x. And what we mean by that is we're using all of the nice functions, or the nice curves that don't intersect each other and they don't loop, and this fails the vertical line test, and it has an intersection point of itself, and these are all bad things and nothing that we've considered so far in the calculus of variation. Every time I have a point here, we call this the independent variable, and then I will get a dependent variable, which we call f of x. So we do have 2 points every time, x and y, but when it's on the graph of a single function on that type of curve, we're going to get the point x f of x, or xy is what we're getting. Now what we want to do is describe more complicated functions, but it fails the vertical line test and we can't write y equals f of x. And in other cases, you saw probably when we did volumes of revolution and surface area of revolution, or the area between curves, sometimes they would write cleverly x equals a function of y. But that's not going to help me. That's just flipping the roles. That's just turning your head 80 to 90 degrees and then doing it this way. It's just rotating. It's just interchanging the roles of x and y. So that's not going to be getting any good either. What we want to do with parametric and polar is describe the points on the curve in the plane R2. We want to describe those points x and y as both being functions of another parameter t, which is going to range between a and b in some interval. And this is why we call them parametric. So now instead of having points on a curve in the plane, and how we describe them is an independent variable, and then y equals f of x is the dependent variable, functions which pass the vertical line test. Now we want to describe curves which fail the vertical line test possibly, but we would still want to do calculus and have descriptions of them. All of the interesting functions are these type of functions, turns out. What are we going to do with that? Instead of doing this business and writing x f of x for xy, what we're now going to do is get a different parameter and call this one f of t and g of t. We're going to let x be a function of t and y be a function of t, and now every point on this curve will be, as t moves in the interval, we will trace out values or points on that curve. Let's give the formal definition of that. Definition: let x be a function of a parameter t and y equals some function g of t be continuous for all t inside an interval a b, which I'll most likely call I most of the time. The set of all points x, y, which are specifically f of t, g of t, all of these points, the collection, actually the set of all of these things, we're not going to call it anything, but it would be like the graph gamma. When we do the graph of a function g, that's all the set of all points x, f of x, such that x is in the domain A, we say, and that's the graph, but that's because it passes the vertical line test. Now what we're describing is the same thing, but we're describing the x and y coordinates as functions of t, remember. Parametric curve, and we write, basically I'm going to write it like this: x is f of t y is g of t, where a is less than t is less than b. Now, what this describes is, instead of the graph, it's describing the set of all points that are going to trace out that curve, whatever we're going to get, and then we're going to find out, cool, we're going to get the infinity sign, or we get to finally use calculus to describe some of the symbols in calculus, the lemniscate, those types of things. This is the definition of what a parametric curve is versus the regular curves we've been using in calculus. One more time, the regular curves, gamma is what I'm going to call this. A lot of the books use C, but I'm going to use gamma for graph or curves in the plane. Either way, the regular gammas that we've been using were nice functions where we could write gamma as an explicit expression, y equals f of x. This is our technical definition. Again, what is it doing? For a regular curve in the plane in calculus so far, x is the independent variable, y is the dependent variable, and we can write gamma as y equals f of x, and then that means you get a nice plot that you've always seen with your functions, and it passes the vertical line test. Now we have horrible curves in the plane that don't pass the vertical line test and self-intersect themselves sometimes even, and we are going to cleverly write them like this. Instead, we're going to write the ordered pairs as functions of time which range over something, as t is the parameter of the curve, and also p f of a g of a is the initial point, and q f of b g of b is the terminal point of this curve. So it's where you begin and you end. This will become important eventually. What we're going to try and do here now still is we're going to have cool lemniscates or the infinity sign or those types of things, and what we're going to want to do still with calculus is find the derivative or the equation of the tangent line at any point to that lemniscate, or we may want to try to find the how much string do I need to make a bunch of infinity signs, or what's the arc length of this, and we need to talk about an initial point and a terminal point of the curve when we trace it out, and make sure that we trace the curve exactly once when we go through our parameter. See what's going to happen, especially when you see when we do polar coordinates, we're going to get all these clever cardioids and all kinds of functions, and they're going to do this type of thing, and that's why they're called cardioids. But as we go from our parameter, if t is going from 0 to 2 pi, say, but then I have an extra r equals cos 4 theta or something, and I've extended the period or something like this, we need to know if we've traced out a full revolution or whether we've compressed the period, and whether we go around and trace the curve more than once as we do that. And this is what polar coordinates are going to do. They're a parameterization which will be useful for specific categories of functions. Let's do a couple of examples. So we have a straight line. Basically what we're going to do is I'm going to remind you how to build the y equals mx plus b form. I'll build you the regular Cartesian where x is the independent variable and y depends on that. And then for a straight line, the easiest parameterization is to just set x equal t, and then y is a function of x and therefore a function of t, and then I have a parameterization. Let's do that. Basically what we have in the plane is, first I draw this 1, 2, 1, 2, not to scale, but I have the point 1, 0, it says, and the point 2, 2, and this is gamma. Of course, this also, I've started with one which is the graph of a function in the plane. I'm trying this weird machinery and new description. You can do it for every function. Every curve gamma can have a parameterization. Even functions are curves, so they can have a parameterization too. We just have a regular way of doing it, and then what we want to do is extend that to nastier curves which are not the graph of a single function, like circles and lemniscates and these types of things. So who is this guy? Well, I have the point 1, 0, and I have the point 2, 2. So how do I build the equation of a line? I need a point and I need a slope, and then I can use the point slope form to build this. I already have 2 points. I'm flush with points. I need the slope. The slope is rise over run, change in y over change in x, which is 2 minus 0 over 2 minus 1, which is 0, 0, 0, 0, 1. and they're not equal. 2 over 1 equals 2. So our slope is 2. That tells me once I have a point and a slope, y minus y1 equals 2x minus 1, or y equals 2x minus 2. This is the classic way of x is independent and y is dependent on x, and I can describe every point on this curve now by putting point x in from 1 to 2 and computing values. And that's exactly how I'm going to parameterize now. What we're going to say, therefore, is this is the old classic way. This is the Cartesian or the graph version of this. You'll see why I'm calling it Cartesian, because this is not the polar expression of points in the plane. Polar is going to, instead of talking about x and y coordinates, we're going to talk about a radial distance and an angle theta, r and theta. And then we start doing calculus and everyone's a pirate, arty, arty, theta. How do I describe the parametric expression of this same curve? This is the Cartesian avatar of this geometric avatar. What is the parametric avatar of this beast? This curve gamma now is cleverly not equals, well, he is, but we're going to write it like this. X I'm just going to let be the parameter, and then y is 2t minus 2. Now you can see x is a function of t. He's the identity function, but he's still a function of t, and y is a function of t. And where was t going? T was the same as x, so x was going from 1 to 2. You may find this amusing, but in engineering 209 multivariable calculus or 215, or in these classes it may be called something different, but in where we're teaching, this is what they're called. But in multivariable calculus, they're going to make you do line integrals and all these types of things, and you have to do line integrals over arbitrary curves gamma, and they'll give you this, and then you're in a multivariable calculus class, but you still can't set up a straight line and then parameterize it. So this is how you parameterize a straight line. Get 2 points on the line, create a slope, create the equation of it. I set x equal to the parameter and then y equals the other one. There's other ways of doing this. The parameterization isn't unique, but we'll get into that another time. Let's do another one. Reversing this, let's give us x equals t squared and y equals t plus 1, where t is in R. So now they've given me the parameterization. This is the parameterization, or if you want, what we're going to say is this is gamma, is what they're saying. They're lazy in the book, and we write left to right, top to bottom. So it's convenient to write it horizontally, but this is actually, we're writing this as the f of t, which is t squared in this case. It's nice to match the theoretical wah wah. You pick up the phone and it's Charlie Brown, and what does she say? Wah 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 wah. It's like, oh, I don't want to hear. Yeah, that's what it's nice to match what the kids are saying to what the horrible parents are saying. It's always the parents on the phone, the kids don't. It's just wah wah, white noise, which I know is what I sound like when I do this. I'm doing it anyway. There's the parameterization where t is negative infinity is less than t is less than infinity. Now what I want to do is, let's give the Cartesian description or avatar. I'm going to go reverse. In the first one I just did, I gave the familiar first because I'm reliant on that. I built the familiar y equals mx plus b form of that line, and then I cleverly did a parameterization, and then we get the parameterization of gamma. Now they've given me the parameterization of a curve gamma, and I want to go backwards, and it's actually going to be easier to write x equals a function of y instead of y equals a function of x. How are we going to do that? Luckily in these can get extremely complicated, and the game will be slightly different every time. But in this one, I see x is t squared and y is t plus 1, which is a linear equation in 2 unknowns. If x equals t squared, and I want to get rid of t, I have 2 equations, and I want to eliminate one of them. What I'm going to do is, in this one, I'm going to write t equals y minus 1, and then put it into t squared. X is equal to y minus 1 squared. And now what is this? It hurts your brain, but turn it 90 degrees, and who is this? I've interchanged the roles of, you're used to seeing y equals x minus 1 squared, and who's that? Shifted to the right 1 unit. That's correct. So now who is this guy? When I interchange that, that's a parabola, but he's on his side, and which way is he going and where is he shifted up to? That's correct. Now what's happening? The vertex of the parabola is up 1, and then, actually let's draw this to scale. At 0, we're going to cross, I'm going to believe, and then so what am I going to get? We're going to get dot, dot. This is gamma in the plane. You can plot some points again if you can't see it, but this is what's happening. It's a parabola on its side. Notice now what we have done as switch and why this is extremely useful. This is no longer a graph. This is a square rooty function, we would call this, because this is now, we never talk about x being a function of y. We always said y has to be a function of x and it has to pass the vertical line test, not the horizontal line test. But this is not a function. Normally what we do is we get rid of it and we call it square root. We pick the positive square root of this so that it will become a function. Now we're not concerned with that at all. This is the curve, and we have a parameterization of it. So that's parameterization of curves. Next time what we're going to do is the calculus of parameterization of curves. So what we're going to do is formula for dy dx and d squared y dx squared, the first and second derivative of y with respect to x when they're parameterized. And then we will do arc length and trace the arc length of parameterized curves. Please hit the subscribe button and the notification bell. It will update you on videos to come, and check out the other playlists and a bunch of videos that we already have. This is the Tutor Wizard. I'll see you next time.